Hello everyone. Thank you, Efim Mikhailovich, for introducing at least me. Let me introduce my topic. In this case, it's subnanosecond switching of standard thyristors triggering in impact-ionization wave mode by high voltage PCSS driver. The work was carried out in SIAME laboratory of the Universite of Po in France. And first of all, here I would like to thank organizing committee of this conference for opportunity to speak here. Also, it's my pleasure to give credit to my co-authors, such as Prudaev from Tomsk State University, Ivan Lavrinovich, originally from Institute of High Current Electronics. Now he works with me. I'm very happy about it. Also my colleagues from Po University, it's Anton de Ferron and Pecastaing, and Novac from Lavrinovich. So, let's get started. No, I also want to thank Institute of Electrophysics, because this topic, this research topic, is originally come from Institute of Electrophysics. My presentation split it into 4 sections. First section, introduction, consists of describing challenge, some research background, and my idea of current research. Next, we're gonna speak about experiment setup, especially about thyristors under study, some trigger generator we're gonna use, and the diagnostic tools that we used in this research. Then section devoted to results obtained. We can split them also in 2 categories. It's with current flow and without current flow. At the end, some conclusions will be done, and I hope we have time for a few questions. So, introduction. I'm not gonna talk about plasma, fortunately or not, I don't know, but I'm gonna talk about some devices that can create finally plasma. And for pulse power generator, switch is the key element, and many requirements like this. It should be reliable, replaceable, and so forth. And normally people who work with them want use affordable, so it means cheap devices. Nobody wants to buy expensive, sophisticated stuff for pulse power generators. Possible solution might be thyristor, also known as silicon controlled rectifier. But the main challenge for this device is relatively low DIDT capability from the pulse power point of view. For example, standard thyristors provide us about 1 kA per microsecond. There are several solutions to increase this parameter. One of them is parallel connection with well-known disadvantages such as current distribution and trigger synchronization of triggering. Another solution is sophisticated structure like GTO-like structure, so integrated thyristors. They are very good, except the price. And another technique of triggering high voltage solid state devices called impact-ionization wave mode, which I'm gonna talk today. A little bit basic of semiconductor physics. In order to switch, I mean to turn on semiconductor devices, we have to create plasma inside the semiconductor region, base region, and one of the most classic mechanisms is current injection. Unfortunately, due to saturation velocity, we cannot achieve switching time faster than 10 nanoseconds in high voltage devices. Impact-ionization wave mode, discovered by Dr. Gusev and colleagues in 1979, roughly, showed that creating impact-ionization wave inside of semiconductor structure allows achieving of switching time less than 1 nanosecond. It happens because of front velocity, in this case, much faster than saturation velocity in silicon, for example. Later, by Dr. Rukin, it was confirmed for standard thyristor that impact-ionization wave mode can be realized in thyristors you can see on the leftmost picture. Standard thyristor, low frequency thyristor of tablet design. In the middle of this slide you see voltage curve across this thyristor during impact-ionization triggering and switching conditions for this mechanism. So, if we can increase voltage across the thyristor with voltage rise rate more than 1 kV per nanosecond, and at the same time we can reach doubled value of static breakdown voltage, we can realize impact-ionization mode and obtain switching time less than 1 nanosecond. In this case, it was about 200 picosecond. Based on these experiments, the prototype of semiconductor switch was designed, tested, and parameter reached listed on the slide, and you can compare the obtained current rise rate with datasheet parameters. Moving on. Main idea of this project is try to not use big and normally expensive and sophisticated pulse generator to trigger as well as big thyristor, but going into a low energy region, let's say, and using lower generator, cheaper, more simple generator, and try to trigger standard thyristors in TO package. And as far as I know, nobody tried before, so we found this topic quite interesting from both scientific and possibility of application sides. Let me describe experimental setup. This is an overview, just how should experimental test bench looks like, in my opinion. My students don't agree with that. They do mess all the time. Let's dive into detail and talk about parts that we tested, especially thyristors. What is the most common thyristor, you may ask? I would answer that those you can easily find in the lab. So as soon as this is work, I say pioneering work for these transistors. So we don't have any recommendation in the literature what kind of thyristor we should use. That's why we use our previous experience, and we decided to take thyristor with rated voltage about 2 kV. So 5 types of thyristors were chosen with rated voltage from 0.6 up to 2.2 kV. Pretty standard, except maybe this one is a little bit exotic, but this one is very, very common thyristor. Parameters listed here. I'd like to draw your attention to the DIDT parameter, and normally it's less than 0.3 kiloamps per microsecond. We continue. Speaking about trigger generators, we used 2 of them. One of them is off-the-shelf generator, so it's standard model. The second one was tailored. Start from standard model, it's FID generator, proudly produced in Germany, but I believe this technology came from St. Petersburg, obviously, from laboratory of Dr. Gusev. Nevertheless, this generator works perfectly fine and deliver to the load pulses with following parameters. The most interesting part for us, it's adjustable output voltage from 1 to 5 kV. Another generator we used, it's designed specially for us in Tomsk State University. We call it PCSS generator. Parameter on dummy load, also listed here. The main difference between 2 generators is the price. If the first one cost about 10,000 euro, the second one 10 times less. So we're pretty happy to test the second one as well. Few words about circuit and principle of operation of PCSS generator. It consists of several modules. The most interesting for us module is switch circuit. On the slide it is highlighted in red. So here you see appearance, this is just diagram, and electrical circuit, probably the most interesting part. If we zoom a little bit, we will see that switch circuit contains three main semiconductor elements. First of them, it's high gain photoconductive semiconductor switch made of gallium arsenide with rated voltage of 1 and 3 kV. We ordered two types of this switch, and current about hundreds of amps. It's designed and manufactured in Tomsk State University. The second device, it's a pretty standard laser by Osram, semiconductor laser. And the third device, S-diode, also gallium arsenide device, developed and manufactured in Tomsk. And in my opinion, this is the most interesting part, because this diode allows convert relatively slow pulses up to DC into sub-nanosecond pulses. Unfortunately, I don't have time to explain everything about S-diode, but I encourage you to read publications about this diode, because previously it was used in microwave domain, but now with increased voltage and current, this device is more or less suitable for pulse power applications as well. Okay, diagnostic system includes voltage probe, homemade voltage probe, that connected directly to cathode and anode electrode of thyristor. And the data signal from this probe is treated by a train of high frequency, wide bandwidth, high voltage attenuators and digital oscilloscopes. Again, few words about this probe. It's not our invention, unfortunately, because it's quite clever. Basically, it's resistive divider with high voltage arm represented by carbon ceramic resistor, partially shielded by braiding of 50 ohm coaxial cable. It was suggested by Belkin and Shudzenko, and from the original work you see parameter of this sensor, its construction and the optimization process. Because to obtain this parameter you have to optimize length of braiding that actually compensate parasitic inductance of this resistance. Our sensor, we tested it with FIT generator, and we obtain following parameters. I should note it here that 1 GHz is limited not by sensor itself. It's limited by FIT generator because rise time 350 picosecond. It's the shortest rise time we can obtain for calibration. So we can say that at least 1 GHz provided by this sensor, but normally it's a little bit faster. Moving on to the results. Let me skip first failures and go straight to the first successive result when we trigger 1.6 kV thyristor with FIT generator. In this slide you can see two situations, one of them without bias voltage, so we don't apply any DC to the thyristor, we apply immediately triggering pulse. And the second situation, bottom part, is bias voltage. We biased it with rated voltage about 1.6 kV. As you can see, in both cases we observed stable triggering with switching time around 200 picosecond. And it was measured by this sensor that previously showed 350. That's why I told you that it's not limit of sensor, it's limit of generator. Next, we try all 5 thyristors that we have using FID generator as a trigger source. Again, in 2 cases, without bias and with bias voltage. On the left side, you see thyristors from 0.6 green curve up to 2.2 kV thyristors black curve, and 1.6, 1.2, 1.2 in the middle. Unfortunately, we cannot trigger, as you can see, 0.6 and 2.2 kV rated thyristors without bias voltage. So you see the voltage is rising and then very slow decay. It's not normal situation, it should be like this pretty fast. However, applying bias voltage, we can see that all 5 thyristors were successfully triggered. Possible explanation of, let's say, failure in the first case might be quite high equivalent capacitance of them. And it means that trigger generator just not powerful enough to quickly charge this capacitance of thyristor. Because when we bias them, capacitance decreased dramatically and generator is sufficient. Next, in this experiment we test 2.2 kV thyristor in 2 modes. Firstly, we fixed output of FID generator at 5 kV level and we change bias voltage from 1 to 2.8 kV. You may ask how we can apply 2.8 kV to 2.2 rated thyristor. Normally manufacturer give this rated voltage with some margin. So normally it's 80–70% of real static breakdown. The same with the 1.6, we can increase voltage up to 1.8, 1.9 roughly. The second experiment was fixed bias voltage at 2.2 kV level and the variation of triggering pulse from 1 to 5 kV output of FID generator. What is the main conclusion of these 2 experiments? That the main factor, in our opinion, that leads to fast triggering, fast switching, is voltage amplitude and electric field inside semiconductor structure. We cannot directly measure electric field, but we can assume that higher voltage we measure before switching, higher electric field inside structure. And this high electric field leads to faster switching time and less residual voltage. So you see the extreme case when there is no switching, extremely slow decay and pretty high residual voltage. Moving forward. The same thyristor, 2.2 kV, but triggering by PCSS generator. Without bias voltage, no switching at all, but we can see that increasing charging voltage of capacitor C1, so it's basically voltage that applied to thyristor after switching PCSS. So the higher this charging voltage, the faster rise time and the higher voltage amplitude we can reach. So it's logically to assume that we need as much as possible charging voltage on this capacitor. Then we apply as much as we can, as we could, bias voltage to this thyristor, 2.7 kV. And also we were close to, now it's good. 2.63 kV charging capacitor. And we were close to triggering this thyristor by PCSS generator, but still you see the triggering is not good, but it's better when charging voltage higher. So we try to go above the limit, even though manufacturer, I mean Tomsky, say no, you don't need to go higher than 3 kV, but we say we need it. We go and at 3 kV, no problem, 3.4 kV, failure, breakdown, surface breakdown across PCSS. So now we're working on more high voltage PCSS. There is some problems, but I hope we're gonna solve them. Then we're going to experiment with current flow after switching. For this case, pretty simple RLC circuit have been developed. Consists just capacitor storage, some resistor for damping oscillation. We don't need reverse current through thyristor. And measurement current shunt, pretty standard with SMD resistor and SMA connectors. Important part is choke, magnetic switch, we can say. It serves for decoupling current part from triggering part. Otherwise, without this choke, we lose trigger power because it's spending to charge this capacitor instead charging of thyristor capacitance. Principal limitation of this circuit is DIDT up to 19 kA per microsecond based on short circuit experiment. With FID generator we obtained following parameters. So DIDT increased up to 300 times compared to datasheet parameters. We tested 1000 pulses at 1 Hz with no degradation, but I know it's not a number for solid state switches, but we were limited by pulse repetition frequency 1 Hz and it takes time, so further investigation of lifetime of course is planned, but for now it looks like it works. And with PCSS generator and 1.6 kV thyristor, not so exciting results, but still 100 times improvement of the IDT, and again 1000 pulses at 1 Hz, no degradation neither PCSS nor thyristor itself. Switch to conclusions. To sum up, I'd like to highlight that probably for the first time it was demonstrated that standard high voltage thyristors in TO cage package have been triggered in the impact-ionization wave mode. Some improvement of the IDT parameters have been reached, and in our opinion one of the best thyristor from these 5 types, it's 1.6 kV thyristor. Concept of using PCSS generator as a trigger generator have been proved, so we still gonna work on PCSS design and its component construction, but nevertheless we show that in general we can use this generator to trigger thyristors. And some observation, in our opinion, extremely low and extremely high voltage thyristors is not a good choice. So it's better to choose something in the middle. We could not achieve the fast switching at DVDT less than 0.6 kV per nanosecond, and this is in perfect agreement with the literature, where it stated that 1 kV is the minimum, 1 kV per nanosecond. Again, from the basic consideration, if you want to make life of trigger generator easy, you have to apply some bias voltage. Once again, electric field, not DVDT, is the main factor, so we have to reach certain amplitude, not DVDT. But actually, high DVDT leads to high over voltage value. Further plans, as I said, it's improvements of PCSS, testing of 5-6 kV PCSS. To be honest, they already tested, but I don't want to present these results right now. They still have to be treated, analyzed, and properly presented. But we obtained it, it works, and we obtained much interesting result with high voltage devices. And the next step ahead, it's test of high current switch, because this is just 10 nanofarad capacitive storage. Now we tested up to 100 nanofarad with current up to 1 kiloamp instead of 100 amp, and the IDT also a bit increased. But again, it's topic of my next speech, I hope. I hope you found this presentation interesting, and I would be happy to answer your questions if you have any. Thank you.